Hello, Honors Chem. I know that I am not there today, but just pretend like I am, and I'm giving you the notes over this lovely video. So today, we're going to be talking about intermolecular forces, which would be the attractions between molecules. So what this picture is showing you here are the different attractions with the hydrogen to the chlorine, but notice it's not necessarily a bond, but because of the partially positive charge on the hydrogen, it's attracted to the partially negative charge on a chlorine in a different molecule. Now, if we were talking about intramolecular forces, which we have been, we would be looking at the bonds in each individual molecule here. So intra would be looking at the bond between hydrogen and chlorine, but what we are looking at are the attractions between the two molecules in general. So that's summarized here. So in intramolecular forces, we've been looking at the bonds inside molecules. So intra means inside, inter means between. So here we're looking at the attraction between two or more molecules. Kind of force with intra, it's a bond. With intermolecular forces, there is an attraction between various molecules, two or more. The function for bonds, obviously, is to help hold the atoms together inside the molecule, but for intermolecular forces, this keeps solids and liquids from changing phase, okay? Because if these did not exist, they'd be in trouble. Strength. These are stronger just because there's more energy needed to break bonds inside molecules. But intermolecular forces, they are weaker because they do take less energy to break. And obviously there are eventually phase changes, but they don't happen as quickly if these did not exist. So the first one that I'm going to talk about are dipole intermolecular forces. And essentially what's happening here is there is a covalent bond in all of these molecules, whatever they are. We don't have them labeled, so I don't really know. But what you'll notice is the positive end is attracted to the slightly negative end in another molecule. So what's happening here is between polar molecules, so all of these are polar, right? There is an attraction between them, okay? And just like the negative end attracted to the positive end here, the positive end is attracted to the negative end here. And you notice they are between the different molecules is what we're trying to picture here. Now this only happens between polar molecules, not nonpolar. Why? Because nonpolar molecules don't have a partially positive and a partially negative end. There is no dipole at all in nonpolar molecules. So this is only in polar molecules. Now there's an even greater one, okay, called a hydrogen bond, where that's still between polar molecules, right? And here's like a water molecule. Here's the slightly negative end, and then the hydrogens have that partially positive end. So the hydrogens are attracted to the oxygens of a different molecule, and the oxygens are attracted to the hydrogens in the different molecule. So this is an attraction between a hydrogen bonded to either a nitrogen-oxygen-fluorine in one molecule and a nitrogen-oxygen-fluorine in another molecule. So hydrogen bonds, these types of attractions are only going to exist if there's hydrogens that are attracted to nitrogens, oxygens, fluorines in another molecule, and they have to contain nitrogen, oxygen, or fluorine. London dispersion exists in all atoms and all molecules. So even if it's polar, non-polar, whatever, these are going to exist in every single type of molecule. So out of the three, this one is going to pop up in all of them. So if you're ever asked, what kind of intermolecular forces are there in this molecule? Every single one is going to have this. There's always some sort of attraction, okay, between molecules. But this is probably the weakest one. Well, it is the weakest one, okay? So London dispersion forces are weak, and they're in all molecules. Dipole has a moderate strength, okay? And that is only shown in polar molecules. Hydrogen bonding is the strongest, And this exists in polar molecules with an OH bond, an NH bond, or an FH bond. So it has to be one of those three types of bonds, or else these will not exist. So the way this looks on your practice, okay, that you have in front of you. So all you're doing is you're listing all of the intermolecular forces from strongest to weakest present in each substances. So you're going to look at that first one, right? That's octane. And you got a bunch of carbon-hydrogen bonds here, which we already know, hopefully, is nonpolar. So these are all nonpolar bonds. So the type, sorry, I'm trying to get my pen to work. The only type of intermolecular force here is going to be London dispersion. I'm just going to write LD to keep this short. So since it's not polar, it's nonpolar, it won't have dipole-dipole. It won't have hydrogen bonds. Okay. I'll do this second one with you too. Okay, so immediately I know it has to have London dispersion, right? Because all of them do. Now if I look here, okay, all of these bonds, the carbon-hydrogen bonds, those are going to be nonpolar. However, there's an oxygen right in the middle here, okay? So here's a polar bond, here's a polar bond. So dimethyl ether is going to have some polarity with it, and that center atom also has lone pairs on it. So this is also going to have dipole. Sorry for my atrocious handwriting, but you get it. Okay. Now, the last one I'm going to look at is hydrogen bonding. So I have an oxygen here and I have hydrogens. However, in order for this to be a hydrogen bond, this oxygen would have to be bonded to one of these hydrogens, which it's not. So there is no hydrogen bonding in this molecule. It could only be that way if the hydrogen was directly attached to the oxygen. I hope this helps. Do the best you can. The answer keys should be in class. If you have any questions, let me know and I will try to get back to you as soon as I can. Thank you.